Get in there. Let's get in there. We live? Hello. Hello world. Hello universe. Hello, hello, hello. Alright, so to continue from where we left off last time, we finished on number 67. So let's look at 68. I think 68 was pretty simple. Not much to review here. You kind of just process this bit. I think I explained it, so I won't go over that again. 69, let's see, I'll know if I explained already. More merge with a function, yeah, I explained that. 70, let's see if we did that. Word sorting, I think I explained this. This is pretty succinct, pretty cool. Let's see, 71, intervals. Wait, what happened? Oh, that's right, because that's not 71. 72, 73. Yeah, there's tic-tac-toe board. I think we explained this one. It's pretty cool, this solution. Pretty cool. How about 74? Filter perfect squares. I think I explained this as well. Right, a sub-function determines whether or not something is a perfect square. 75. Toshin function. Yes. So this is, right, brute forced. I think I explained this last time as well. 76 is trampoline. Did I explain? Yeah, we went over the. Okay, so this is kind of cool. We'll go over this again. I think I explained this as well yesterday, but we'll say. Yeah, we'll say we actually had to. Yeah, the other day we actually had to implement this. It's interesting. This is interesting. Right, it calls this function, which returns this function, which then calls this function, which returns again another function, which then calls that function, and each time you got this x, y, y, where you're conjoining with x, a y, and we called it initially with an empty, what do they call it, an empty sequence, empty vector, and conjoin with a 1. So we end up with 1, 1. Then we said if the last of this, which is 1, is greater than 10, it's not. You're gonna return this function, which then, because you're using trampoline, you call this function, which actually calls this one again, which returns this one, which then calls this one, which calls this one, and you sort of jump back and forth repeatedly until the last value in x is greater than 10, and you end up adding 2 to whatever the initial y was, which we start with a 1, so you end up with 1, 3, 5, 7, 9, 11, and that's the point at which you're greater than 10 and you return all the stuff in x. So there you go. Yeah, fairly straightforward. Now if we go to 77, the Anagram Finder, now this was very interesting as well, and you could have used a group by here. I'll show you what the group by would have looked like. It would have been, you also don't need to use a sort, you can use frequencies. So what you can do is, if you group, so let's say, I'll show you this works. I think we talked about this one too, but you could have used, instead of a reduce, you could have used a group by. This is kind of cool. And you would have used frequencies, and that would have also worked. No, didn't work. What? Excuse me? Really? Oh, you gotta sort them though afterwards, I believe. You gotta place these into sets afterwards though. Yeah. I think that's the problem. The part that I'm missing. Try that. There we go. Okay. So you could also use a group by and then map set to the results, but I kind of like what I did initially. Kind of prefer it. Although it's definitely a lot faster if you use the frequencies. It's faster and it's technically potentially more efficient. Like I didn't actually need to use the sort of W for this key. Although this is kind of the same thing as using, if I used frequencies here instead of sort, it's kind of the same thing as the group by. This is basically a group by function here. Pretty cool. Anyway, so yeah, that's cool. That's a good time. So 78, we get right implementing trampoline. So this is kind of interesting. Now look at that. Isn't that concise? I think we talked about this too. So this is someone else's solution, but this is like super interesting. So this is, you gather the inputs. So you have a function and a bunch of arguments, right? And then you apply this function to those arguments, and you get the result of that. And then what you're going to do is filter the result of that into this iteration, which is which iterates using this function, which is a function that takes a function and returns the application of that function, given that function has no arguments, right? So this application should return a function, then we supply that function to this iteration, and that means that this iteration is going to generate this function which calls that function. And then basically, how does this work? This will actually call this function on what you give it. That's what it is. It calls this function on what you give it, which means that you'll give it the result of the first call, and then it calls this function on that, which means it calls that function, which obviously this returns a function, and that function has no arguments, right? So then this gets called. Then the result of that is yet another function, and the next iteration applies this function again, which calls that function, which returns a function. So you keep calling functions until this drop while basically keeps calling these functions over and over until you get something that's not a function. So you keep dropping things from the sequence until you hit something that's not a function. And then finally you take the first thing of what's left over that sequence, which is just, yeah, the thing at the front of the sequence, which is something that's not a function. So really concise way to describe the trampoline function using functional programming. This is like, talk about functional programming. This is it. This is really cool. It's really cool implementation. Also, I improved this slightly because they used only two arguments, whereas in reality the trampoline function could take any number of arguments. It could be variadic, and so you actually need to rewrite it a little bit differently. Use apply and this syntax. So I guess they didn't think of it, but yeah, pretty neat, fairly neat. So let's move to the next thing, which is 79, and I think that's where we stopped at. Yeah, so this took me like all day to realize, to think about, to put this together. And I actually like my solution more than everyone else's solution for this. Everyone had like a different way of solving this. I'll explain how to solve it. I'll explain what the problem is. We'll talk about it. So really we're starting at like 79. The other problems we just kind of briefly went over just to double check that we did them. But yeah, this is a very interesting question. This is a very interesting question. And also a lot of stuff to talk about here, and in particular, I like the way that I solved it more than how others solved it. There are some other folks they solved it in an interesting way, but it's a little less obvious how they did it, and I think that makes it kind of not that great because of that. Yeah, there's a very concise solution to this that I took some time to try to understand. We'll go over it also now, and I'll try to explain and understand how that was done. But that, although it's concise, it's not really obvious what's happening, which makes it kind of hard to read. You know, it's like like your code should actually be easy to understand. Like that's really what you want. Concise code is typically very easy to understand, is easier to understand because it just doesn't have a lot of stuff going on. But in this case, it seems like there's not enough explanation. More so, it seems like there's not really enough like why does it work, like understanding the why and what it's doing. So I'll show you this solution. This is like kind of a generalized approach to like dynamic programming, but let me explain. So we have this triangle minimal path. Let me save this as well. Let's go to our notes, coding. Oh, okay, coding note. Oh, I know what happened. I moved things. Hold on. I moved things around. Somewhere in here we want coding notes, I think. General notes, coding notes, I think this is the one. Yeah, there's a whole boatload of notes here. I don't really have a spot for the 4Clojure notes. I guess we could make a spot for the 4Clojure notes. Oh wow, so much stuff, man. Can I do this? It works. Cool. All right, we'll put it right in here. Coding notes 4Clojure. We'll say, what do you call this? It's minimal path. Minimum path. All right. So basically, you end up with this. So I'll state the problem first. Let's start with that. So also we can put this up here too. So let's start with stating the problem. So write a function which calculates the sum of the minimal path through a triangle. The triangle is represented as a collection of vectors. The path should start at the top of the triangle and move to an adjacent number on the next row until the bottom of the triangle is reached. So as an example, you got 1, 2, 4, 5, 1, 4, 2, 3, 4, 5. And you might take 1, 2, 1, 4 to the bottom, or 1, 2, 1, 3, right? 1, 2, 1, 3 at the bottom, and that gives you 3, 4, 7 as a solution. And the other minimal path they give you is probably 3, 5, 6, oh maybe not, actually it looks like 7, 10, 7, 10, 12 maybe, 18, it's not so obvious. They give you the answer. Let's do the algorithm that I would normally do. I would say, let's see. Well, actually, yeah, okay. Well, it's actually takes a bit of computing, believe it or not. You could do it by hand, but it takes some computing, realistically. So when you have like a lot of numbers, it's kind of becomes somewhat prohibitive. But anyway, they give us the answers: 3, 4, 3, 4, 3, 2, 7, 1. That gives you an answer of 7, 10, 12, 19, 20. Right, so 20 would be the answer. 3, 4, 3, 2, 7, 1. Okay. Now, how do we solve this problem? Let's start with just how one solves it, and then that'll inform our algorithm. So let's take this one. Let's take this one. Copy. We'll use text here. All right. Oops. Oh, I guess we're not. Okay, that's fine. What is going on here? Hello? Alright, whatever, we'll just do it this way. Okay, sure. So, if we have this initially, right, what we want to do is say, all right, let me rewrite this like so. Because this is actually how like a machine's going to look at it. And we'll note something here. So the deal is, you really only have two options from where you are. You can really go down or to the right, 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 right, down, and then or to the right. No matter what position you're in, those are your only options, right? And what that means is that from any spot that you've got, actually let me undo all that. I should keep a pristine copy here so I can copy it. Whenever I want. So you've got down and to the right, no matter where you are your only options. So there's only two options in each of these cases. Now the thing that's interesting though is that implies the only options you've got for if you're looking at a particular bottom position, the only options you have are either directly above or above and to the left. Right, you've got two options to pick from. And what you can, and now the inductive argument for this algorithm is actually very simple. It's that if you knew the optimal path to both of these positions, then you can easily find the optimal path to this position by simply taking the smallest of these two possibilities, because there are only two possibilities, and then adding 7 to it, adding this to whatever the minimum is. And that would be the path to take. And it's inductive because you don't necessarily know the optimal for these. But if you did, then you could find the next. And obviously if you knew the optimal for the entire row previous, then you could find the entire next row, right? Because you can just apply that logic to each one by one. And that's really the core of the algorithm. It's actually really simple once you realize that. And so the technique that I'm about to describe to you is a common kind of dynamic programming question technique that's asked a lot in interviews. And what it boils down to is you can basically take every problem of this nature and suggest, okay, as long as I have this inductive step, all I've got to do is write a recursive function that finds the pieces I need recursively, and then memoize, perform whatever operation required to get the next step, and then memoize that function, right? That recursive function. And what will happen is, in some cases, you might end up with very, very bad runtimes, and basically the memoization doesn't do anything because all of the pieces that you're calculating in between are unique. But in this case, it's very clear that the only things you need is right above, and that's actually not a lot of information in order to compute the next step. So the memoization in this case actually works out very nicely. If you needed more information to compute the next step, something like that, then the memoization wouldn't work so nicely. And that's for like exhaustive search algorithms, which some algorithms basically all we know of as far as solving them is an exhaustive search. That's like your NP-hard type problems fall into that category. Basically, the memoization would be kind of useless. Dynamic programming would be kind of useless in those cases, or it seems to be, because the choices that you have to go through are all unique, more or less. They all don't have any information that can be used to make the other computations faster. kind of. That's sort of the issue with those questions. But in this case, it's very clear that the previous computations can be used. There are previous computations we can make to easily get the next set of computations. And that's the core of the algorithm. It's really simple when it comes down to it. And the reason why I like the way I programmed it, more so than anyone else, is because although you could easily compute, do a reduction that basically computes each of these sort of next sequences, right, based off of what the previous sequence was or is, which is what the really concise versions do. While you could do that, wouldn't it be more, I guess, more general form? I guess it'd be sort of like a more general form if you said, okay, I'm going to compute each of these pieces, but each of these pieces, really, I only need exactly these two elements, right? For this element, I only need these two. Yes, this whole thing I can get using this whole thing, but I could also just get each of these individually and then process them at the end. And each of these individually comes down to this, and then each of those is this and this, and so it creates a very nice kind of recursive dynamic programming problem. It's very, very, very clean in some sense. Now the problem is, and I'm gonna try to explain this locally here. Try to explain what I did and what you're seeing here. This is pretty. It looks kind of huge, this code, and kind of ugly, but it's not that bad. But I'll explain it piece by piece. So let me just indent it. Oh no, undo that. Oh shucks. I don't really like this indent. I keep pressing this accidentally. I've been doing that all day. Anyway, so one insert, one indent. So what we get is this. Okay, we got this triangle path, triangle. Now, what I want to explain is, first, let's start with, okay, I said you've got this recursive function that's very simple. It just takes. Oh, wait a minute. Did we? Oh. Got this recursive function. It's very simple, and it just takes. It really only needs to consider like three pieces of information, right? The value at the position you're currently at, and recursing on either on both the position above and the position above and to the left, right? That's all you need to know. The thing about this, though, that makes this kind of complicated and kind of confusing is that memoization in Clojure is not nearly as clean. Well, it's relatively clean, but it's not quite as clean as it is in Python. Python, you can literally just add a functools, what do they call that? A functools, what's that called? It's not an operator, but it's got a name. What's it called? Let me think for a moment. It's not a keyword, not a func name. What the heck is it called? It's an annotation. What is that called? Hold on, let me go find it. Python functools memoize. LRU cache. That's what it's called. But it's also a decorator. That's what they call it. Okay. So as a decorator, you can wrap your functions in Python. That makes it very efficient, very easy to memoize them, right? Obviously, it's literally one line. That you write your function as it is, and then you just add LRU cache, and you're done. Obviously, what memoizing is, for those of you who don't know or are curious what I'm talking about, memoizing just means that when you call the function, given certain inputs, you get a certain output. Well, when you memoize, you call the function, it computes this output, and then it does that one time, and then the next time, and then it saves those inputs and that output into probably a hash table. Usually, more likely than not, a kind of hash table. Saves those values, and the next time you in a cache, the next time you call the function, it doesn't recalculate the value. It just returns what it computed last time, which is extremely effective when you're dealing with functional programming and functional functions, in that there's a certain guarantee that every time you call the function with a certain set of inputs, you always get the exact same output. So it's very easy to memorize, or it's very effective to memorize. So there's a certain so anyway, what this is going to do is make our recursive function a lot more efficient. Now that's right. So like I said, in Python it's just LRU cache. You're done. In Clojure, it's a little more work, and there's kind of some explaining to do here. So let me start with, so how did we end up memoizing this? Well, there's a memoize function that you have that you give memoize a function, and then memoize says, okay, what we're going to do is when you call the function that's returned by memoize, it'll do exactly as I described. It'll call the function you gave it that it wraps, which will then execute and compute a value, and then after that it'll save the value. And then the next time you call it, it'll actually get the cached value rather than calling the function again. Now you may when you think about it though, you realize that there's some problems with that. So in particular, if you call this, if you call memoize on a function, it gives you a brand new function. But note, we're trying to use a recursive, and I have the answer here, sort of, but we're trying to use a recursive function which has a name, and we're trying to call that function again, which means that this thing that we're calling is not going to be the memoized version, it's going to be the original version, which is a problem if you recurse that way, because let's say if you have something like the Fibonacci sequence, which has exponential running time if you do it recursively, the first calculation will take forever because it's only calling the original function repeatedly, and so that takes forever, and you never actually get to memoize anything if you don't do it in a special way. But yeah, if you try to do it that way, where you're calling the function that you've defined recursively, if you don't memoize at all, obviously, then that's no good. If you memoize after the fact, that's not going to work either, because let's suppose, like the Fibonacci sequence, we want to actually memoize as we're calculating, not just for the first element. And finally, and I can actually show you what I mean by all of this. Like let me actually show you. It's better that way, I think. Let me show you exactly what I mean. So watch this. I'm going to write a Fibonacci figure. I showed one of my coworkers this earlier. We were sort of between things, and let me show you exactly what I mean. So Fibonacci sequence is really simple. Basically, it's take the last two numbers that you calculated, add them together. That's your new number, and repeat that. Iterate until the end of time, right? So we'll say we have if n is less than or equal to 1, then we'll just return 1, right? So if it's 0 or 1, we return 1. Otherwise, we're gonna get Fibonacci of n minus 1. This is decrement n, plus Fibonacci of, we're gonna decrement twice n, right? And then finally return here. Says one extra. Oh no. Oh, because this should be here. Okay, got it. Right. So that's a very simple Fibonacci sequence. Now let me show you what happens if we call Fibonacci of 5 and then call Fibonacci of 50. You should see this very quickly, and we're also going to add print lines here, so that way we can actually see what happens. What you'll notice is if we line run, let's exit this, line run, right, watch what happens here. It takes a moment to run. So it prints 8 immediately, right? So 1 and 1 is 0, 1. then you have, so 0, 1, then you have 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, right? So the 6th or 5th, in this case it's the sort of the 6th Fibonacci number, or if you're counting from the 0 index, 5th would be 8, right? 50, on the other hand, like I said, this is exponential. This is basically going to take forever. It'll almost never, not that it won't ever terminate, but it won't terminate anytime soon. And so you see it's just halted there. It's just stalling, right? And let's actually exit. I don't want that to keep running. So you can see that this takes a very long time, right? Now, if we tried to memoize this, and we'll take another Fibonacci sequence, and we'll call it Fibonacci function, and we'll call it Fib2, and memoize it by defining Fib2m as memoize of Fib2, right? If we try this now and do almost the same thing, similar thing, you'll notice, I call this Fib2m, you'll notice we actually end up with the same problem, and we'll just comment this one out, these two out, so that way we don't get stuck, right? It should be exactly the same thing we get. It takes a few seconds of line run. See, 8, and now we're stalling again. Same problem. This is what I was describing. If you memoize after the fact, it's not going to work the way you would like it to, because this needs to memoize as it's calculating, not afterwards. It's not very useful afterwards. We want to do it in tandem. So you have something of a problem. But it's not, it doesn't seem to be that big of a problem, because you can just say, okay, let me be clever here. We'll call this Fib3, right? And then what I'm going to do is I'm going to memoize here, right, outside of this function. So now we have this memoized function, and I'm going to define this Fib3m, which is now memoized, right? Sort of combine these things, and we're going to call the memoized function here. We're going to recurse on the memoized function. So we have this function named Fib3, which uses these symbols inside of it, and then we're going to memoize on that function, and then we're going to declare this symbol to be, hook this symbol up to the returned function here. And it seems kind of like circular reasoning a bit, because like this isn't defined. This is being used before it seems to be defined, which seems confusing and contradictory, but it's a bit abstract, and it's also lambda calculus and functional programming. It works in kind of a different realm, let's say, and although it seems to be circular reasoning, it actually works. You can actually do it this way, which seems really odd, but it's possible. It can be done. For whatever reason, the compiler does operate reasonably well with this, or actually can do this. The compiler can do this. Oops. Undo that. For whatever reason, it does work. So let's now take a look. What happens if we use 3m, right? This is kind of neat. I mean, I kind of gave you the answer that it does work, but let's see what happens now. So we'll give it a moment to start. And there you go, boom, took almost instantaneously, right? We got this value that we were looking for. So now you say, okay, that's all well and good, but there's a problem here still. There's still a problem, and that problem is this is defining this fibm3 in the entire namespace, in this namespace, which means that I can't use fibm3 anywhere else in my program, anywhere else in this namespace. It is quote-unquote polluting the namespace. Meaning if somebody else somewhere else decides to use this fibm3 for something else and defines it again, then this function won't work properly anymore, which doesn't make any sense. So you can't do it. You need something better. Well, what you do when you want to define something locally, so it's not in the greater namespace, is you use a let, and this bindings will bind effectively to declare variables and bind them, and then inside here you can execute using those variables that you defined. Right? That's what the let does. Excuse me. That's what the let form does. Excuse me. There's even a let fn, which we actually won't be able to use for what we're going to do. But let's stick with the let. So what it turns out you've got to do, what ends up happening is what you need to do in order for this to work properly is the following. First, you declare your function, right? So we've got our fib3, right? Now we're gonna call it fib4, we'll say. So you got our Fibonacci function, and what we're going to do, this is interesting, is we're going to say fib4, but we're not going to call fib4 in here, right? We're not going to do this. What we're going to do, and we're also going to memoize this as well, right? So memoize this. We're going to take our function fib4, and we're going to go ahead and say, give me a function here, right? So there's two things going on now. Instead of just taking a number, you're also going to take a function. So fib4 takes a function and also n. And actually, you don't even need to name it anymore, by the way. You don't even need to name this. So we'll make it anonymous. We'll get rid of fib4. And what you're going to do is you're going to say, okay, call that function f and provide f again to itself. So we have this anonymous function, which takes a function, and we call that function. We don't know what it is, and we also supply that function to itself when we call it. And we do that in both cases, right? Now, what's going to happen here, and we take this whole thing and we declare it aux, right? And we memoize it, declare it aux. And it seems kind of confusing at first, and it is confusing, but what's happening is you're basically providing this function f to every function call. Every recursive function call has access to f, whatever f may be. And we have our logic in our body here. We're going to say, take this anonymous function that performs this Fibonacci sort of logic and memoize it now. So whatever function that was, it's now memoized as well, and we return that as, we would declare that as aux. Make that aux. Now what we do is we take aux again and rebind it to this aux function, which is this function. But we're going to provide as a first parameter. I'll tell you what this partial does. This first parameter is aux itself, right? Is this function. And what's going to happen is interesting. What's going to happen now is this memoized function. So what you did is you said, okay, and then you're gonna rebind aux, and you're gonna. So I'll explain what partial does first. So partial takes a function and an argument and says, this function, assuming it has at least one argument when you call it, we're going to bind that argument to this function call such that when you call the partial, it already knows the first argument every time. So basically, that's like saying, let this f be aux, right? Whenever you call this partial, let this f be defined as aux. So then it's as if you replaced f everywhere in here with aux, which, as we know, aux is already this memoized function, which is actually exactly what we want. We want it to be using this memoized function, and you're gonna say you're gonna bind this aux to what we already had, this memoized aux function, which took two arguments, this function and n. So now we bound f appropriately, and then we're going to rebind all of that to aux. So now it's like sealed, as we don't have access anymore. Now this function is what we wanted. This is this Fibonacci memoized Fibonacci function, where now it doesn't take two arguments. It only takes one, which is n, right, at that point, after we've bound itself to it. So really, really abstract and really like kind of hard to wrap your brain around, but that's how it works. Pretty cool. And now we can call print line within this scope. we can call aux of 50, and we can call aux of 5. I thought that was super interesting, this whole shindig. And what we'll see is now both of these will execute very quickly, and we can run that. I'll show you that now. There you go. It's very quick. So that's what memoization looks like in Clojure, whereas Python obviously is just LRU cache and you're done. There even, I think, is a macro you can write to memoize recursive functions, which someone wrote on a Stack Overflow post. So this is pretty cool, pretty interesting. Took me some time to get my brain around, but I appreciated it. And what we're going to do is now consider. So this is the technique that we're going to use to solve our problem. And the reason why you want to do it this way is that you want to use this recursive function in your local namespace. And the reason why you can't just define a value here the way you could in the global namespace is that when you try to call aux, if you just tried to put aux in here, it would say it's not defined yet, which is true. Hasn't defined this in the local space yet. Whereas somehow in the global space it does get defined before this is called, which is really odd, but that's just seems to be how it works. So yeah, and right, obviously you want to put things in the local namespace so that way other things don't interfere with it, and so it doesn't interfere with other things. Ironically, if all of your code is in the local namespace, then you could put things in the global namespace because it wouldn't interfere with any of the things in the local namespace. Sort of. Not kind of, it's a weird how that works, but you want to keep everything in the local namespace anyway, just because you don't want to arbitrarily have something muck up your functions when changes are made later. If it's not necessary, you don't want to do it. So there you go. That's how you do that, how you perform that. And we're going to use that technique in our function. And I'll explain what our function does. So our function in very simple terms is our function in simple terms takes the triangle, right? So a defined triangle path takes a triangle which looks like this, right? And then it converts that into a vector because it could be a sequence, the triangle, but places it into a vector. Each piece, so that way we can actually do a lookup for any element, right? And then what we do is, excuse me, you see the memoize, you see this f of ij, right, this function. So we're going to memorize this anonymous function, this auxiliary function. We're going to say if I is less than 0 or j is less than 0, so basically if we're in nonsense land, just return 0 immediately. Otherwise, we're going to define a let, which is there's going to be an above and above to the left. So these are going to be your recursive functions, which basically takes indices. So our auxiliary function and some indices. The above means the same j index, right, where j is the same column, but I is the row, right? And actually, probably could have made this even simpler by using row and row and column. Yeah, I think that would have been better. Actually, I should have done that. That makes it a lot more readable. So above is a row above, and above and to the left is a row above and a column to the left. Decrement the column and decrement the row. Define those two things recursively, right? And it's memoized, so it's efficient even still. And then we're going to say we're going to get in this triangle. We're going to iterate over the row and the column. Now this get in will actually first get from the triangle using row, which is going to give us the whole row, and then it'll apply the column within that row, which will give us the value at that position. And then if it doesn't find it, just gives you a 0, because it doesn't. Who knows what's going on if you can't find it. This should handle those cases. It could be malformed. Like Obviously, this doesn't do a lot of robust checks on the form of your triangle. Your triangle could be arbitrarily shaped, in which case this code won't make any sense. But assuming you give it pretty good format, your format doesn't have issues, which it could. But assuming it doesn't, what you're going to do is you're going to get the value at the position you're interested in, and you're going to add something to it. And what do you add to it is depending on the conditions you're looking at, it will change. But if you're looking at something if you're looking at the very top element, all the way at the beginning, the 0th row and the 0th column, right? Sort of the first row and first column, then you don't add anything to it. You just take that element and you go on your merry way. If you're looking at the first column, though, and you're not looking at the top element, then you can only go directly above, right? Because I think we showed that earlier, that if you're looking at the first column, there's only the thing above for the path, and if you're looking at the last column, similarly, the only way you can reach this spot is from what's above and to the left. So we say, if we're at the first column, we can only go above. If we're at the last column, which is here, the nth value of the triangle, let's say, so that's actually I is row. So actually what we're doing here is we're getting from the triangle, we're getting the last row, and we're getting the size of the last row, and we're decrementing by 1 to get the index of this value. Yeah, so if this column is all the way at the end of the row, right, it's the last index of the row, then we perform this. We return this value, which is recursively what the best path above and to the left is, right? That's here. So this recursive, right? And then if none of this works, right? If we're just somewhere arbitrarily in the middle of the triangle, then otherwise we take the minimum of the best possible path above and the best possible path above and to the left, and we add the minimum of those two values to the value that we're looking at. And that's it. It's like super simple, the logic, extremely simple. We do all of that recursively, and we memoize it, and we use that trick that we described earlier, where everywhere you would normally just put an aux, you put this ff instead, and you bind aux to aux, and then now your function just takes a row and a column after that point. And yeah, also we rebind triangle to a vector of these sequences rather than a sequence of these sequences. Really, it should be a sequence of if we're given a sequence of vectors, we want a vector of vectors in order to use this operation nicely, as well as some of the others. And so finally, you say, okay, well, all we've got to do is compute the optimal path to all of the values at the bottom of the triangle, and then just get the minimum of those optimal paths. And that's exactly what this does. This says, all right, first let's just have a let to give me the last row. Really, it's this gives me the index of the last row, and then this will give me the size of the last row. And then we say, okay, let's repeat the index. It really should just be like index, last row index. And then this is the size of the last row. So we're going to repeat the last row. So we're going to get all of the coordinates of this triangle, right, of the bottom row, and we're going to say get the last row index repeated with the repeated and combined with the range from 0 to the last row size. So basically, you're going to pair off. So if like the last row is, let's say, of size 5, you're going to pair off, and the last row is sort of the 4 is the index, the last row. You go 4, 0, 4, 1, 4, 2, 4, 3, 4, 4, right? All of those values. And we're going to map list to all of these to get us that sequence of all those values sort of combined. And then we're going to call aux on all of those different pairs of values and also apply across them. So because they're going to be sequences of 2 values, a whole bunch of these sequences of 2 values, apply is just going to consider them to be arguments. So then we call aux with each of those arguments, right? Create a map of all the values you get, and then that's just the sequence. That's the sequence we wanted, which is the optimal path for each of those numbers, and then we apply minimum over that just to get the smallest one, and we're done. And you do all of that in a threading macro, which means that this initial result is just going to be what you supply all the way to the right of each of these functions. There's only 2 of them, and it seems kind of complicated, this part, but it's actually pretty simple. It's just saying give me the bottom row and all the coordinates of the bottom row. That's basically it. Give me all the coordinates of the bottom row, run this auxiliary function for each of those coordinates, and then that'll give you the best possible path you can get to that using those coordinates to get to those points, and then take the minimum of those best possible paths. Then you're done. Then you're done. Then you can move on to, then you're done. Yeah, that's it. That's actually the whole algorithm. And I like this a lot better than the other ones that are used here, because the other ones, they're more concise and they're simpler and all of that, but they're not. It's not really clear what's happening, and it's not really like generalizable either. Like, this is kind of a generalizable approach to problem solving, where you can pretty easily just figure out the pieces that you need to go from one step to the next and memorize those pieces recursively. Excuse me, and then this is just sort of one extra processing step at the bottom, which, excuse me, I probably could have made this a little bit simpler. Maybe I could. I'm not really even sure if I could. Maybe I could just take. Nah, not really. You can't really make it that much simpler. It's pretty simple though. I mean, it's not that bad after all. Like, it's very clear. The last row index repeated with the range over the size of the last row, and then you just got to pair those off into lists, sequences, and then apply those apply aux to the sequences. Obviously, aux was defined specifically as like aux of ij, such that you can easily, given any row and column, or not ij, given any row or column, row and column, you could easily figure out what's the optimal path to that point. And that's why you have to gather up these points at the bottom. But this is pretty simple what it's doing overall. So yeah, it took a lot of words to explain that, but that's what's going on. So yeah, pretty cool. Pretty cool. I'm impressed by the solution. It's not, like I said, it's a lot more lines than is really necessary to solve the problem just solve the problem directly, but it does illustrate the more general solutions. So the more general problem solving techniques that would be lost if you did it the other ways, because the other ways kind of gloss over those things a little bit, sort of. And I'll explain what I mean by that. So let's open up the next row. So let's go to the next. Let's go to 80, right? Yeah, perfect numbers. Okay, so this is where I stopped, and I want to show you. So this is one of the solutions that's very, very concise. Basically, what he did is he used a reduction. He first what did he do? He first reversed the list, so you're actually going from the top part down to the bottom, right, rather than the other way around. And instead of it being like a pyramid, it's like an inverted pyramid. All right, flip the triangle on its head, and then the reduction basically does what I was describing, which is take the you want to find the optimal path to, actually it looks like I think this goes the other way. This does something kind of funky, but basically all you need is the whole vector of the previous calculations, and then you can easily get the next calculations. I don't actually know what he did here exactly. It's kind of weird. But what I think he did is he said, give me, he said in this reduction it's going to take, so the reduce is these red, down is what you're sort of changing at each step, and up is going to be the next element of that. So what I think he did was he actually said, instead of giving me the optimal path down, give me the optimal path in the other direction, going up, from the bottom up, right? I think that's what he did. I think he did a bottom-up approach here. And he said, okay, give me that vector, and then we're going to do a minimum of that vector and the same thing, but one less element, right? Like, I still haven't really fully processed how he did this, but if we use something like, let's do like these numbers, right? But this is kind of what I'm getting at, where it's like it's not really clear what he did, you know? Like, even though it's very concise, it's like it takes you a while to figure this out. Whereas here you could say, I could just add comments that say, you know, if you're in the first column, only consider what's above you. If you're in the last column, only consider what's above and to the left. Otherwise, consider recursively what's above and what's left. And it's kind of clear you're adding what's there to the minimum of those two values. So, let's continue. Whoa. What we want to do is flip everything over, reverse it, and just kind of perform those operations, and we'll see. So if you perform these operations, what this did is it said take the minimum of this down with the rest of down, which means it's going to look like this, which the minimum is going to give you 9, 2, and 2, right? And you don't consider the last part. All right, map takes the smallest collections, the smallest of the collections, and it applies. So what it's going to do is it's going to say map minimum on down and rest of down. So down and then remove the first element of down, and those are the two collections. And so you're actually going to have one less element as a result of this, which gives you 9, 2, and 2. And then you're going to actually add all of these values to what's in up, which in this case is 1, 9, and 3, right? So then you have plus 1, 9, 3, which gives you 5, 11, and 10, right? And that's kind of interesting. I don't really understand, because, oh, okay, I see. So yeah, so it's going backwards, but the thing that's happening is you have these two things to consider. You say, okay, pick the smaller of these two and add it to this value, and that's happening on a vector basis. So it's happening sort of at every point. Like taking this minimum of these two collections automatically figures out which one of these is the minimum to be added in this case and in this case. And what's interesting is you actually don't consider, in the last case, I think is the one that's not considered. No, you can do, I think it's, no, I don't know. You do compare 4 with 2. So you can get to 3 with 2 or 4. So I think what's happening is this is already decided. No, so all of these have possible values, right? I'm not sure. There's, see, this is interesting. There's one. I think because we only end up with 3 numbers at the end of this. But why 9 with 9 decides the first number, right? It's between these two. Then 9 and 2 decides the next number, which is 2. And 2 and 4 decide the last one, 3. So yeah, I guess it is that simple. It's literally just, there's a number that we don't consider here. Like, why? I'm confused. No, it's not that we don't consider that number. It's that we don't care to, like, you get 9, 9, 2, 4, the comparisons. Or no, the other way around. Yeah, you lop off this first element and you compare 9, 2, and 4 this way. And so you only compare 9 once to something else. This first 9, which is the next value. I don't actually know how to describe this. I don't really know why, like, I wouldn't have thought of it this way exactly. But basically you're comparing all these elements to the next element, which is done by actually shifting them all to the left 1. And you don't care to actually compare the last element to anything else. Because you don't need to, right? You only need the first 3 elements anyway. So yeah, it's a pretty clever way of doing that. But basically, yeah, you take what you've already got and consider that the next vector has got to pick from either the one above or the one above and to the right. And then so what you do is you compare those 2 values, which is the one above and the one above to the right, by just taking this juxtaposition of all this sequence of values and the same sequence with the first element removed, right? Everything shifted over to the left 1. Do all those comparisons while also losing one element at the end, and then that's what you're going to add to the next vector, right? Because the next vector, you're always going to have to, if you're at that position, you're always going to have to add that value anyway. So you can just add it directly, and that's it. And you just that's the reduction you perform. You do that repeatedly until you end up with what's at the very, very bottom, and then you just return that'll just be a sequence with one value in it, you just return the first to that sequence, which is just return first. So yeah, extremely concise, really simple, very concise, but not quite so clear. You know, like, it took a while to really process all of that. And it's not super general either, because it's not a recursive, it's not memoization of a recursive function. It is, but it's very what's the word? It's done in very large chunks, such that you can't really see it obviously. It's not so obvious what's happening here. Yeah, it's kind of like, I don't want to say it's an optimization, because it's not really that much more optimized realistically. And it's maybe a little bit more optimized because you don't have to memorize for every single path. It only uses that one vector repeatedly. But it's not that much better, really, because you're using that one vector over and over again anyway. So it's like the amount of space that you need, it doesn't really change that much. The amount of processing you're doing doesn't change much either. It's just a little bit less clear, I think. I think that's the problem, is that even though it's very concise, it takes a little bit of thinking to like really understand what's happening, and it doesn't just memorize a recursive function, which is, you could put the logic in there very explicitly and memorize over it, and you're in good shape. Yeah. And obviously this could be written in a functional way, but it's just easier to use the above and above left as names. These would, if you're doing if you're memoizing properly, excuse me, even if you put the function calls right in there, it would still be efficient because they'd be effectively constant time each copy, because they're just cached. So yeah. Yeah, the running time of this is obviously just, it visits every element once, and that's it. It's linear with respect to the input size. But yeah, very concise. Glad I understood it, glad I saw it, but definitely kind of a lot to unpack here, and kind of take some time to really understand what's happening. It's not like super explicit what the logic is, whereas the logic is extremely explicit. And you just memorize over the recursive calls, and it's like super simple, super easy. Yeah, this gives you a general approach to all of your dynamic programming questions, right? So like there's a lot of interview questions where they ask dynamic programming type questions, and basically you can do this almost for every one of them. It'll seem really hard at first, but once you realize what it is, it's pretty easy. All right, so moving on. Yeah, it took a while. Spent like an hour just reviewing all this, but that's okay. I mean, it's pretty interesting, this whole shindig. How to memorize a local anonymous function or just a local recursive function in Clojure. Right, that whole spiel is definitely interesting. So let's do the next thing, and that would be perfect numbers. Okay, let's actually try to solve some of these problems. By the way, we're also officially past the halfway mark. We were at 156. The total is 156, so minus 80, 76. Right, 76 was the halfway. I don't know. I don't know. It's 156. 78 was the halfway mark. Yeah. So, okay, perfect numbers. A number is quote-unquote perfect if the sum of its divisors equal the number itself. It's perfect if the sum of its divisors equal the number itself. 6 is a perfect number because 1 plus 2 plus 3 equals 6. Write a function which returns true for perfect numbers and false otherwise. Oh no. So, I mean, actually enumerating the divisors of a function is not as difficult as you think, I think. Is that right? I don't remember. Enumerating the divisors. Yeah, actually enumerating the divisors is kind of interesting because you only need to check up to the square root of that number, and that'll give you every divisor. And then you can actually sum over all those values. So we can do this in square root of n time, which is kind of neat. Yeah, so let's look at how we might do that. I mean, yeah, okay, yeah. Square root of n time might be what? So we could do a loop over those numbers in that range and sum all those values. Now, how would we know if it divides? We just do modulo. So we would need square root. We can do the floor of the square root plus 1, I think is the way to do it. Or the roof of the square root. we'll do the roof of the square root, a range over the root of the square root, and then just add 1 because the range lops off that value. So we'll just do the ceiling. So how do we get ceiling in, I think it's math/ceiling. Can we do that? I can try that. Let's open the REPL here. And let's try to get the square root. So what this will be is like you take this range over something like this, math square root of, I want math ceiling, and convert that to an integer and increment it. So increment, I could even do one of these. So it'll be increment int math square root, and we could throw this in here, and it'll be math ceiling, right, all of that of some input number. So we get this range. Actually, range will be at the very end. So it's kind of a lot going on here. And then, right, so we get the square root, take the ceiling, convert it to an integer, increment by 1, and take the range. And then, I want to throw that in our REPL. And then, we're going to take this, obviously it's an anonymous function, we're going to take that thing, that range, and say we're going to filter, could even filter one more time on what? The filter is going to be modulo, so we'll use this anonymous function. Probably should do it this way then. N, say function N. We're going to filter on modulo as 0. Right? So n modulo this value is 0, which means this divides n. Filter on that. And finally, summate over those things, which is apply sum. And then we say take that what's left and add and say if this result equals n. And return that. And that's it. And that's it. Yeah. Actually, that might just be done. No. Oh. Okay. Let's throw this in our REPL. Does this work? Let's do like 100. Don't know how to create iSequence from Java Boolean. Am I missing anything here? Also math square root, math ceiling. I wanted to check those. Clojure, square root. And then Clojure, ceiling. Java maybe. I don't have ceiling here. Shucks, also so loud. Whew. How do I? Okay, math square root. That's fine. And we're looking for. Yeah, precision is the issue, or at least one of the problems here. But math square root is. So I want to take the ceiling of it. Math ceiling Java. Yeah, we should be able to do ceiling. That should work. Why this doesn't work though? Sequence from Boolean. Let's try this. Let's just see what we end up with if we do this. Given n. Like if I did this operation, range of increment of int of math ceiling of math square root of 100. Perform this operation. What does that give you? All right, good. That's what we expect, right? That's what we're looking for. Now, if I try this, of 100, okay, that is not what we're looking for. Is it the other way around? Maybe that's the problem. Maybe this needs to be reversed. That would be kind of annoying. That would be really annoying. Right. Yeah, of course. All right. Got it. Understood. See the problem. See the issue. See the problem. Going backwards now. Uh-huh. 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 Right. Right. Okay. Okay. Think I see the issue. 5 by 0. Nice. Nice. The range needs to have a 1 in there. Obviously. False. True. Okay. Cool. So, you know, I just kind of did the wrong direction. Oh, 496. What do you mean? What do you mean? What? Whoa, 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 whoa. Whoa, 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 whoa. Excuse me. False. How do you figure that? 31. What? 1, 2, 4, 8, 16. 496 is 2. This would be 249, it looks like. 48. 248. That's 124. That's 62. That's 31. Oh. What's the square root of, well, 496 minus divided by 31 is 16. I see the problem. I made a mistake. I done goofed. Yeah, I screwed up. It's kind of interesting. So you actually have kind of a problem doing it this way. It's not that simple. You actually need all the divisors. What's the square root of 496? It's kind of confusing. If you take 496 and divide by 2, you get 248. 6 divided by 2 is 3. Square root of 6. Oh, I did it wrong, huh? You actually don't want to increment this. Confusing as that may be. Yeah, but what if you do like 49? Alright, 7. And you do like 8, right? So we can do this. We can add another filter in here and just say filter this thing squared is less than or equal to n, right? So we can include, you know what we're going to do also? We're going to go ahead and start doing this. So it's a little more clear what's going on here. Yeah, so filter on the things that are less than or equal to this square root. And the problem here also is we want to create a set as well. Right, remove any duplicates. That's so 49, we take the square root, we get 7. We don't want to have 7 twice as a divisor, just 7 once. And we also want filter on the divisors, right? Create a set, or no, filter on the divisors. Then we're going to, this is going to be interesting. It's going to be this function, which takes, actually I want a map really. It's not really a map, it's like an interleave. That's what we want. Interleave between, it's going to be n divided by the value and the value. How do we do that? How does this work? So each of these values, we want to create a sequence. What's a map, right? It's going to look something like this. Can up, or just map divide n. I guess n divided by x. Apply that here to the sequence. Interleave that with the values themselves, the divisors. Create a set out of that. I think that's what we want. Yeah. And then we want to check. I'm going to add all these together. Check if it's equal to n. And then apply that to 496. Yeah, that's a doozy, man. That's a doozy. Nice. At which point, where's the issue? We can do something like this, right? I think this is no issue. Yeah, no problem here. As soon as we add this piece, small problem occurs. So this is the one that causes an issue, it seems. Not clear why. All right, let's take this interleave and we'll say f of n, and we're also going to call this anonymous function with, so let's call that with I don't know, n is like 100, and then we're going to call this anonymous function that returns with a sequence of like, I don't know, 5 and 10, right? And just see what we get. So we get 100. Okay, what? Let's make this 100, right? Do it this way. Yeah. What does this look like? Also, what is this percent going on here? This is kind of confusing. This function mapped here. Oh, there's an interleave. That's why. So let's remove the interleave. Let's just see what we get if we do this. Map and remove f of n, and just call this anonymous function here. Okay, 2010. That's what we expect. Now, if we interleave this map, right, with the original, what do we get? 25, 10, 10. Okay, so that's what we wanted. How is this different from this function? It's exactly the same function. Nice. What? Can we create a set out of this? Yeah. That's fine. What is the problem? Where is the issue? What is going on here? Excuse me. Excuse me. Excuse me. N is something different now here. Now that's a question. Maybe it's the macro that's causing an issue. Right, there's this original N, and then you give N here. I'm wondering, these are exactly the same. I have the right idea. I have the right idea. Well, what do we have at this point? Right? Put that in there. And then we got 496. What do we get? What? All right. Close this here. Close it one more time for f of n. And 496. Close last one. Okay, good. 1, 2, 4, 8, 16. All right. Now let's add interleave in this map here and do the same thing. Close 496. Now, oh, that's why. Because you got to call the function. And that's something I've gotten wrong many times in using this threading macro, is I forget these anonymous functions got to be called. Of course. Seems so simple now. Seems so simple now. False. Right. Wrong. What? Not including the original value, right? I see. Yeah. Okay. Okay. Just dissociate one value. Just throw that in there. Just throw that in there. Don't mind me. Don't mind me. No. No. You're kidding. Can I even do this? Is it the other way around? Maybe it's 496 is... Oh no. No, it doesn't work. Huh. How do we remove? dis G will remove. Oh, dis sock is not what we want. Just dis G, or dis J rather. Aha. Unfortunately, you could do this again. You could use another anonymous function. Disassociate. I think this the as threading macro is which is what I would use instead of using multiple anonymous functions. Doesn't work in the compiler or reader that's being used for oh, come on, man. Doesn't work for the whatever that thing's called, the compiler reader, the reader that's being used in 4Clojure is using true. There we go. All right. That didn't take long at all. That only took forever. That took a very long time. It took me a much longer time than I was expecting. But I forgot about something important, which is, you know, oh, come on, man. What is even happening here? Really? Oh, come on, man. Oh, yeah, I guess that makes sense. Hopefully this works. Nice. So what I was missing, or what I was missing, is what I was missing was the fact that yes, you can enumerate all the divisors by considering the numbers up to the square root, but that's only the first half of the divisors. You need to actually divide into the number to get the other divisor, which is a constant time operation, but it still needs to be done. And then you need to gather all those numbers and then remove any duplicates. So there's a few extra steps in here that I was missing. So you can take the square root, take the ceiling, make it an integer, increment it, take the range of all possible divisors, filter that through, make sure that you're bounded by the square root. This actually is kind of unnecessary, this part, but it's okay. It's okay, I think. We'll keep it. And then filter out on only the divisors, then interleave with the other divisors of n, right? Apply each divisor to get the remaining piece. Filter all that into a set, remove n from there because you're going to have 1 in there, so you're going to end up with n divided by 1 is n, so you'll end up adding n in here, which obviously if you add all these together with n, you won't get n ever, so clearly n must not be included. So remove n from the set, then summate, and then check if everything's equals n. Kind of like way more complicated than I wanted it to be. It's pretty simple, but like just came out more complicated. Didn't intend for that to be that way, but yeah, we can look at the solutions too. See what other people did. Oh, I didn't think of that. Really simple one. Mine's a lot more efficient than this because this loops over all n numbers. But yeah, I guess you could have done that too. I didn't think of that. Oh, that's funny. Excuse me. Yeah, a lot of folks just went over this range 1 to x. Two to 1 over half of x. Interesting. Oh yeah, okay. You can drop the range in half as well. But I like mine better. It drops the range by a square root. It's mo better. It's mo better. Nobody else did the one I did. That's kind of interesting. No one else did the one that I did. Well, what are you gonna do? Everyone else took the easy way out. I like mine better, man. I like mine better. So that's 81 is the next problem. Man, I kind of just want to take a break. Like I've been doing this stuff all day. Like I just want to be a reprobate and go watch things on the internet or go waste my time with something meaningless. I don't know. Go to sleep maybe. It's terrible, man. I'm like, I don't know. I don't even know what to describe it. What's wrong with me, man? What's wrong with me? I don't know what to think of myself. Just like, I don't work hard enough. You know, I don't work very hard overall. Just kind of a schmagoo. It's kind of a schmagoo, after all. Write a function which returns the intersection of two sets. The intersection is the subset. So we implement the intersection. It's a subset of items that each set has in common. Okay. Well, I mean, there's one way of doing this. It's just a reduction over the following. So you say it's even easier than that. It's actually just a filter. Given, alright, so given two sets, you say function S1, S2, we'll say S1, S2, right, filter on, let's say filter on S2 using a lambda that says this is in S1, false if you don't find it. I think that works, right? Let's just see what happens. No. Pass to persistent hash set. What? Excuse me? Does this not do, if it's not there, it'll return false? What am I doing wrong here? I don't know. If I call this on, you know, two hash sets, 1 and 1, right? See how that goes. Pass to persistent hash set. That doesn't make a lot of sense, does it? Yeah, that's what I thought. Why does it do that? It'll return nil otherwise, right? Like, what, S1, S2, so we do this, right? Oh, okay, I guess that works. Maybe we need to make a set out of this, though, at the end of it. Oh. I was thinking that the false would be the default value if it's not found. I think you need to use get in order for that to work properly, for that to work that way. Failed unit test. Nice. Nice. Probably need to create a set out of this. Which is odd, but I guess it is what it is. Yeah, okay. So that seems kind of simple. Basically, you just loop over all the elements in one set, check if it's in the other. Can you really do it faster than that? I don't think so. I don't think so. I think that's, you're kind of stuck with that. It's relatively efficient though. You could take the smaller set and use that one You know, if you really want it to be efficient, do a quick check, swap the order if one is smaller than the other. Solve the problem, see the solutions that the users you follow have submitted. Yeah, let's take a look at the solutions. I bet you everybody did something similar. Oh wow. Okay, sure. What? Difference, set difference. Oh, look at that. The set difference and the set difference. Are you kidding? Look at what people did. Whoa. All the stuff everyone did. Into filter. Yeah, that's I should have used that one. That would have been better. Mo better. Mo better. Yeah, into is better. I forget this. FN, you just do into set. Use filter. What do they use? Oh, really? 1, 2. Filter 1, 2. Wow. How do you do that? Why does that work? What? That works? Oh, I guess it does. Wait, why would that work? Huh? Oh, because the set is a function. Wow, I didn't even think of that. The set acts as a function itself. So you could just filter this set on this set. Oh, that's pretty cool. Why wouldn't you just return this? Oh, because you gotta make it a set. Oh yeah, so you do this too. That's even better. I like that more. Yeah, why would you use into? Cool, good thing we looked at that. Makes these things even more concise. I like that. I like that. Comp set filter. Ah, look at that. You can even do better than that, right? You can say, oh, well, oh, yeah, because filter takes 2 arguments, right? Huh. What if you did this? No. Yeah. Okay. That's even better. Wow, that's really good. Talk about a solution. Wow. Yeah, I like this one. This is the one yeah, well, not that I did it, but did that after seeing a few other solutions. This is probably my favorite though. Filter set, which gives you the two sets, filters one using the other, and then creates a new set. And that's it. Wow, that's pretty good. Okay, I'm kind of blown away by these, you know. I really like looking at the solutions. Okay, next problem. Word chains. Okay. Hard. Oh, great. A word chain consists of a set of words ordered so that each word differs by only one letter from the words directly before and after it. The one letter difference can be either an insertion, a deletion, or a substitution. Here is an example of a word chain. There's a name for this. Word differs by one character. What's the name? Edit distance. Yeah. Levenstein distance. Yeah. This is an interesting thing. This is kind of a well-known thing too, somewhat well studied, I guess. Levenstein distance. Multiple inventions. Hirschberg's algorithm. Computational biology, cool. Maximal global alignments of DNA protein sequences. When was it invented? Longest common subsequence. 1975, wow. Well, that was a long time ago, huh? Edit distance revisited. That was a long time ago, huh? Los Angeles Department of Computer Science, 1984. Wow. Holy guacamole. It's a long time ago, man. So there's Hirschberg's and Levenstein's. We can read these off later, learn these later. But anyway, Conan. Some other improvements. Computational biology, natural language processing, correction of spelling mistakes or OCR errors, approximate string matching. Objective is to find matches for short strings and many longer texts. Duration of small number of differences to be expected. Solve problems beside the computation of distance between a pair of strings and solve related types of problems. Wow. Bounded edit distance of a fixed reference string, Levenstein automata. Interesting. Interessante. Interessante. Generalization of the edit distance between strings is the language edit distance between a string and a language. Usually a formal language instead of considering the edit distance between one string and another. Language edit distance is the minimum edit distance that can be obtained between a fixed string and any string taken from a set of strings, more formally for any language L. String X over an alphabet. The language set edit distance is given by this guy. String edit distance. Language is context free as a cubic time running. Cubic time dynamic programming algorithm proposed by Aho and Peterson. Computes the language edit distance. Less expressive families of grammars. Faster algorithms exist for computing edit distance. Language edit distance is found in many diverse applications such as RNA folding, error correction solutions to the optimal stack generation problem. Graph edit distance, string to string correction problem. Many diverse applications, RNA folding, error corrections, optimal stack generation problem. So this is all well and good. A lot of studying to do, I guess, with all of this stuff. Let me just slow down. All we need is to think of, for this problem, is think about the edit distance. So what this is suggesting is a word chain consists of a set of words ordered so that each word differs by only one letter from the words directly before and after it. The one letter difference can be either an insertion, a deletion, or a substitution. Here's an example of a word chain. So the edit distance is 1 between all these words. Cat, cot, coat, oat, hat, hot, dog, hog. Cat, cot, coat, oat, hat, hot, hog, dog. Write a function which takes a sequence of words and returns true if they can be arranged into one continuous word chain and false if they cannot. That's kind of cool. Hey, that's pretty neat. So what you can do is effectively, so you want to build a graph out of these words, and the graph is going to be, each node is going to be the word, and then you have a link between nodes, and it'll be two directions, right? Unidirectional link, if and only if the edit distance between those two words is 1, right? And we just need to have an algorithm that either calculates the edit distance or determines whether or not we can determines whether or not we can make these words equal to each other with exactly one edit. So we can actually just do a single edit, I guess, for each of these cases. We could check each of these cases directly, and that'll tell us whether, like, we only need to know whether or not there's an edit distance of 1. So we can build this graph relatively efficiently, I believe, by doing what? And then obviously false or true is if this graph is what's the word, connected or not, right? If all the nodes are connected, then we return true, otherwise false. So this could be converted to a graph, sort of a graph problem, really just checking connectedness on a graph representation. Now, building the graph, how efficiently can we do that? Also determining whether or not these things differ from each other by a single edit distance is also another question. That algorithm, how efficient that would be, I think you do that in time, linear with the size of the words, right? Sort of the linear with respect to the largest word, or linear with respect to the size of the words summed. And then also, I don't know what the algorithm would be for that. And then also the building of the graph itself, how efficiently we can do that is another question as well, which I think we have to do this in time quadratic with respect to the size of the set. I'm not sure if there's any other way. Yeah, see, that's a good question. Because we'd want to check the edit distance against all the other values for the first value, and then the same thing for the second against all the other ones, and the third against all the other ones. And, like, how could you know if the edit distance is 1 or not? I mean, I guess you could split these things up into sets of the same length. Excuse me, but that doesn't really help you either, because no, it doesn't really help much, because the edit distance can actually add or delete values, so it could be arbitrary with how many letters you've got overall. Well, actually it helps you somewhat, because you could say, well, only consider the things that have exactly the same number of of characters, the things that have exactly one more character, and the things that have exactly one less character. You could consider those three cases, which does reduce the amount of strings you need to look at a bit, but if you suppose all the characters are the same length, which they might, then right, it's all just substitutions, then you've got another problem. It doesn't matter at that point. Yeah, I'm not sure if it's possible to do it any other way, because in theory, every value every string could be mapped to every other string by a single substitution, in which case you've got a complete graph, and your complete graph, computing that complete graph is going to require quadratic time with respect to the number of nodes. I.e., this graph is not going to be sparse necessarily. It's not necessarily sparse, which means you're stuck with a quadratic times complexity, which is fine for these test cases, and these are pretty small, but it's not really good after all. I mean, with graph questions, it's kind of hard to get away from the size of the edge set. That's effectively what we're dealing with, is just the size of the edge set, which is quadratic with respect to the number of strings. I mean, it is what it is, I guess. All right, fine. So let's do it that way. So we'll just loop over sort of a double for loop. We'll do a double reduce kind of deal. How does that work? Well, we can use a let to define these functions. One function will just be like is edit distance 1. That'll be a function. And then I think what we're going to do is yeah, double reduce or double for loop, double loop. I think it's a double reduce it comes down to. So we're going to say for each value in the set, you're going to check the edit distance between that value and the and all the other values in the set. Well, what would the reduce look like? Well, it's going to be a I think it'll be a hash map of hash to vectors of the string as the key and I guess the function is just if the reducing function is that if you if that word, if the edit distance of that word between the word of interest, between the key and the word is 1, then append it to the vector, and then you get a vector at the end of that. And you associate that vector with the given key. Yeah, I guess the double reduce. That's what it comes down to. And the outer reduction is just over all of these. That function over all of the with an empty hash map and over all of the keys, all the values. Yeah, fair enough. And then the interesting part becomes, so then you need another function, which is it connected, the graph? Right? Once you've got this hash map of determining whether or not it's connected is kind of interesting. So the way that you determine a graph is connected is you take any point and traverse. You could do a summation of nodes, so that's probably the easiest way to do it. Starting from a particular starting point, do a either a depth first search or a breadth first search. Depth first search is easier because you can do it recursively, and you just sum, basically add one, or just add all of the recursive values, what you return, and if you're at a leaf, you return 1. So you would, like, if you were in one inner node that had only leaves, you would end up adding all the leaves, and that would be the value of that inner node returned. So you can do a depth first search where you just add, you effectively count the leaves, or not count the leaves, but count the nodes. It'd be 1 plus the summation over all of the recursive calls. Yeah, that's basically what you do. So you can do and so determining whether or not it's connected is if that summation, right? So the children, obviously you can use the hash map to get the children. The problem with this approach, yeah, no, that should be fine. You just need to make sure. Oh, excuse me. Oh, it's so itchy. The problem with this approach is that you need to make sure that you don't recurse backwards and go in a circle, which you can do. Actually, you will end up doing if you do depth first search. You gotta make sure you don't go back to a node you had already visited. Which that's kind of tricky to do it immutably, or not immutably, but in a strictly functional way. I think you run into a problem where you need to have something that maintains which nodes you've already visited. Yeah, you can do that, I think. I don't think it's that difficult. No, it's fine. You just pass a set at each step of, like, the things you already visited, and you just pass that each step. No, it's okay. You can do that. That's not an issue at all. Maintaining a list of the hash set of the visited nodes, and don't revisit those nodes. Yeah, so that'll tell you just whether or not it's connected, and all you've got to do is compare the sum to the number of nodes. So is connected is pretty simple. Now the only piece we're missing is the edit distance. Excuse me. Which, if I had to guess offhand, and obviously we can use the Levenshtein distance function, right? We can use some of the research that's been done on the edit distance to figure out a way to efficiently determine an edit distance of 1. But I think how we can do it naively, or at least at first glance. I've seen this problem many times already now, but this is sort of seen it many times by now, but this is the first time I've done it in Clojure, certainly. And I don't remember each time that I do it or have done it, I don't remember it. So, okay, one letter difference can be an insertion, a deletion, or a substitution. So check if they're different by an insertion. To check if they're different by an insertion, we can do what? There's a bunch of clever kind of recursive ways to compute the edit distance, but I want to let me think about this here. So a single insertion would be, first off, they got to have a difference of length of exactly 1, which kind of matters and doesn't matter. What you can do, no, it doesn't work, does it? I guess for the insertion, you kind of want to find the point at which you might need to insert something. So you would check if the characters are equal from left to right, or the character arrays are equal from left to right for both arrays. And as soon as you find a difference, it could be the first character, then you say, okay, if I were to suppose that these are now equal, these characters, and then shift forward yeah, I guess you do want to start with that they're only exactly one character apart in terms of time, size, and then you want to check if the character arrays match until they don't. If they don't, the insertion would consist of scrubbing forward the larger string, right? So you want to swap the things that way that you're looking at, you can identify the larger and the smaller. Scrub forward the index for the larger and continue matching. And if you get all the way to the end and they match, then one insertion will do the trick. That should do it for insertion. That's one iteration. A deletion is just the same, except when they don't match, you're going to scrub forward the larger. When they don't match, yeah, if you actually the deletion and the insertion is sort of equivalent, because they're the same thing, because you would either insert the missing character or into the smaller, or delete the faulty character from the larger, which is equivalent, right? In other words, if there's one character that's different between the two, you can either delete that character or insert into the same spot, same position, the correct position, into the other string, the same character. So the insertion deletion is actually equivalent with that check that I just described. So you do that one check, and then the substitution would be scrub them both forward, and suppose that you substituted. Substitution, they have to both be the same length, and you scrub both indices forward once. And if they're not the same after that point, return false. If you get all the way through the character array, then it return true. So there's two different checks depending on the size of the strings. If one is smaller than the other by a length of 1, then you just swap so that way you know the smaller and the larger, and then you do, as I described, check until they're different. As soon as they're different, scrub forward the index in the larger string by 1, and then keep checking. If it checks out, then return true, and that means that it is an edit distance of 1, which is both insertion and deletion cases. And then if this for the substitution, if both the strings are the same length, then what you're going to do is as soon as you see the two characters are different, then you would basically assume that basically it's deleting both characters, or alternatively substituting one character for the other, and then you scrub forward for both of them. But if you've already scrubbed forward and you need to do it a second time, then you obviously return false. So there's a little bit of something we need to pay attention to for both of these insertions and deletions. You need to quote unquote perform one operation and then ensure that you can get all the way through the rest of the array without requiring another operation, which is interesting because you need to remember that you already made the swap, already made the insertion. Also, if they're equal, it's false, the two strings. So you need to actually make that insertion or deletion, but exactly one insertion or deletion or substitution, right? So it'll be exactly one of an insertion, deletion, or substitution. So if the strings are equal, you return false. If if the difference in the strings is greater than 2, the size is, and it's also false. If the difference is 1, then you got to search for an insertion/deletion, and if they're the same size, then you got to search for exactly one substitution. And it's got to be exactly one insertion or deletion. If you hit a point where they're different, then I guess you would. So I guess the way to do this is to recur, like write a recurring function, recursive function that just updates its inputs, and you can just keep a count of like how many insertion deletions you've had to do so far, and if it's more than 0, then you just return false. You just break right there and return false, or stop recursing there. Now, I don't know if that's really functional though. I'm a little uncertain about these recursive functions that are quote unquote functional. I guess they are technically still functional. You provide the parameters to each function. I kind of had a habit of writing something pseudo-functional in the first place, I think. Kind of reviewing how I used to solve these problems. I kind of would do them functionally anyway. So there you go. That's how you can find the edit distance of 1 sort of naively and efficiently, and then that allows you to have that coroutine to build the adjacency graph appropriately, which you can just do a simple reduction of a reduction, and then finally use a depth first search algorithm to accumulate the number of nodes and check that the number of nodes that the graph described by your hash set of children of connected nodes is connected strings is if you do a depth first search over that graph and accumulate the nodes appropriately and check that the number of nodes in that connected graph is equal to the total number of nodes in the whole graph, then you know it's connected, you return true. Whew, that was a doozy. That's a whole lot of talking. I'm planning it out, but that's the basic idea. So we should be able to do this relatively easily, I think. But those are all the pieces. But ultimately that gives you a quadratic time algorithm, which is not great, but it's not too bad either. I'm actually not going to code that here. I just described it for you. I'll probably code that later and then come back and review the code. But it's exactly as described, and that's not too bad after all. Yeah, come back to this later. I kind of just want to end stream and hang out, go to bed. I don't know what it is about this stuff, man. It just feels draining, taxing. Like I don't know how to describe it. I feel like I just slow down when I'm doing this stuff. I don't know. I don't even know how you describe it. Just slowing down. It's a lot of little pieces. But yeah. Okay, let me end stream here. So thank you for hanging out, saying hello. I do appreciate it. Actually, no, I'm not sure anyone said hello today. That's fine. Those of you who are watching, thank you for watching. Talk to you soon. Have a good rest of your day. Have a good week. Today's a Tuesday. It feels like a Saturday, but it's Tuesday. And about this problem, I mean, it's fine. That's the solution. We'll just code it up. It's going to be interesting coding this up. We'll probably learn some stuff more about Clojure. But yeah, thanks again. Talk to you soon.